All right, so yesterday we covered parallelograms and rectangles, which was the beginning part of our quadrilateral, we'll call it a mini unit within the overall unit. And each of them came with their own rules. Parallelograms had 5 things that we could assume to be true if we knew for a fact that they were parallelograms. And then when we learned about rectangles, we talked about how the 5 things for parallelograms also applied for rectangles, plus we had an additional 2 that we could assume as well. Today, we're adding to our list of quadrilaterals, we're adding rhombi, which is just the plural version of a rhombus. And we're also looking at squares. So this is going to expand our list even further. And tomorrow we'll wrap it up with trapezoids, which is another type of quadrilateral that's kind of marches to its own beat, so to speak. And then we'll kind of tie a little bow on it with a nice little reference sheet that shows all the connections and how they're related and things like that. Looking ahead, so that finishes up that little bit of quadrilaterals. After that, we will do surface area and volume briefly, and not with every 3-dimensional shape you can think of, just enough to say, hey, here's some shapes that exist. Here's a few names for them. Here's how to calculate some surface area and some volume. Just like I said, just enough to be exposed to it. So theoretically, you would know how to work your way through different shapes following a similar process. The reason why I don't hound you too much on that is because if, say, in the future, you needed to know the volume of a cylinder, just Google what is the volume of a cylinder, and it's going to give you the formula. All you need to do then is to know the measurements that you would drop in. So that's why we don't spend too much time on those, just because that's something that you could calculate fairly straightforward with a quick Google search. And then after that, Missy and I were talking, I don't know if anyone else heard, probably going to do I don't want to call it a review day per se, before the test for this unit, but we'll do similar to what we did a few units back, where instead of doing a new lesson, I'll have all the worksheets queued up primarily from this unit, but we can go back a little bit further if need be, and just kind of work through any problems we're still stuck on. And then I think that puts us at Wednesday of next week, taking the Unit 5 test, and don't know that we'll be able to fit circles in this term, because I want to make sure we have enough time to review for the final. If we do, it might be like one day of, hey, here's a couple quick things about circles, because they're my favorite shape, second to triangles. So we're reaching the end here rather quickly. Before you know it, this class will be over. So back to today's lesson, properties of rhombi. We're going to talk about them a little bit. Notice that the first 5 there are the exact same from yesterday's as being the properties of parallelograms, excuse me, as well. But I must emphasize, they are not the same as rectangles. That's a very important distinction to make, because I know previously when we talked about rectangles, we just built off of parallelograms. We're doing something similar today, but that does not mean that we're building off of rectangles as well. So the 2 little things that we talked about with rectangles, one of which was all 4 angles in a rectangle are 90 degrees, and the other one was that the diagonals were congruent, do not apply for rhombi. They actually have their own unique 3 to add to the list from the parallelograms. First one is that all 4 sides are congruent. Excuse me. Second is that the diagonals are perpendicular. And that, if you recall, means that they intersect at exactly a right angle. And the last one is that the diagonals bisect opposite angles. So, same 5 from parallelograms. Those are hopefully not too shocking. We used those quite a bit yesterday. 3 new ones specifically for rhombi. We're gonna right there. We're going to use these properties to allow us to work through and find missing measurements given a list of diagrams. So notice that in the directions, it told me very specifically that each of these shapes are, in fact, a rhombus, which means all the properties listed above here can be assumed to be true. So when we take a look at the first one here, we have a rhombus. We've been given, instead of in the diagram, we've verbally been given 2 measurements. JK is 12. JN, which is inside here, is 7. We need to find 4 other measurements. So let's start with JM. What is the length of JM? Sorry? 12, absolutely. Now, this seems a little bit of a shock because previously we were only looking at opposite sides being congruent. But remember, this is a rhombus, and it has the unique fact that all 4 sides are congruent. So all 4 sides around the outside are all 12s. Next on our list is JL.
14.
How'd you come up with that?
Because half of it's 7.
Okay, half of it's 7. And just to make sure we're not accidentally pulling something from rectangles, up above, we should see that the last one there from parallelogram says that diagonals do in fact bisect each other, which means 7 is indeed half. Doubling it would give you the whole thing, which gives us that 14. Next on our list is MN. MN, which is buried inside, it's half of a diagonal, but here's the catch. These diagonals are not congruent because this is not a rectangle. So I have to get a little bit crafty here. So what I'm going to do is I'm going to let my eyes kind of shift focus here. And I'm going to look at the triangle that's hidden inside here, JMN. And I'm going to work with that bit of information because just a moment ago we said JM was 12. We were given JN and something that's very handy here. Because this is the rhombus, those diagonals are intersecting very specially to form a 90-degree angle, which means hidden in there, we have a right triangle of which we know 2 of the 3 sides. So we're going to go ahead and find that third side, MN. So where am I going to put this? I'm going to put this underneath here. So here's my work for finding MN. I have one of the legs. I have the hypotenuse. MN is the other leg. So MN, I'm going to say is X. So I'll have X squared plus the other leg, which is 7 squared, equals the hypotenuse, which is 12 squared. And then I'm going to work through solving it. X squared is just still x squared. 7 squared is 49. 12 squared gives me 144. Subtract 49 from both sides. I believe we get 95. So x squared equals 95. And then how do we find x? Take the square root, absolutely. So ends up, I get x equals
9.7.
9.7. And don't forget, this x was my mn. So mn is 9.7. Last on our list is mk. Excuse me. So mk is the other full diagonal. How could I come up with that one? Multiply that mn by 2. So similar to what we did with the other diagonal, we doubled the 7. We're going to double the 9.7. We should get 19.4. Good. And because I didn't realize I was going to not need to save so much space, I'm going to, oh no, move this over here and get a little bit larger so I can see it later. You don't have to do that. Obviously, it'd be harder for you. All right. Next up, number 2. We're given EF is 23. DF, which is this entire diagonal, is 40. Not a really good way to represent that. Put half on each. So you're saying since DF is 40, that means DH is 20 and HF is 20. That'd be a good way to do it. Makes up the total 40. And I think that's one of the ones we needed anyways. HF, which is 20.
GF is 23.
GF is 23. And how do we know that?
Because all sides are congruent.
All the sides are congruent. Okay, then we're getting in here. Looks like we're gonna have to work through some triangles again. We're looking for GH. So I'm gonna focus on this triangle that's inside our rhombus here. Because it's a rhombus, that means they are intersecting. The diagonals are intersecting at 90 degrees again. So we're working with another right triangle. I'm looking for GH, which appears to be a leg. Do I know the hypotenuse?
No. Yes, it's 23.
It's also 23. That's one of the ones we listed up above. So we're going to go into solving for GH yet again. Or well, using the Pythagorean theorem again. So, excuse me. GH is a leg. So I'm going to use x to represent it. So I'll have x squared plus the other leg squared, which is 20 squared, equals the hypotenuse squared, 23 squared. Go through the process of solving here. X squared comes on down. 20 squared, I believe, is 400. 23 squared. Don't know that one off the top of my head. 529. Going to subtract 400 from both sides. Leaves me with x squared equals 129. And then similar to what we did earlier, we square root both sides and we get an approximate value for x,
11.4.
11.4. So that's my GH, 11.4. And then the last one there is GE, which is the entire diagonal that GH is a part of. So similar to earlier, we'll just double at 11.4.
22.8.
And we'll get 22.8. Good. Number 3, very similar loose use of the rules that we did with the first two. So I'm going to give you these values if you wanted to try this on your own. For VT, you should get 11. UV, you should get 9. RS, you should get 14.2. And ST, you should also get 14.2. Number 4, this one switches gears on us because now we're looking for angles. I'm going to kind of cheat a little bit.
So this is my issues.
It's finding all the, because there's so many probably. Yeah, so angles are certainly more difficult because there's way more of them packed into the same shape than segments. But when I said I was going to cheat, I'm actually going to focus right here in the middle, because what do we know happens when two diagonals and a rhombus intersect?
90 degrees.
They're always 90 degrees. So I know it's technically out of order, but right off the bat, I know for a fact that angle 8
90.
is 90 degrees. Now, to help me through this diagram, one of the things I'm going to probably use quite heavily is the fact that it follows the same rules as a parallelogram, which means that opposite sides are parallel, which opens up the door for the fact that maybe we have some alternate interior angles in here, which will help me match things up a little bit. So two sets of parallel lines. The diagonals then can also behave as transversals, which means we have some, like I said, alternate interior angles. Excuse me. Another thing that happens, interestingly enough, is one of the new things with a rhombus. Number 3, what did number 3 say up above? Oh, well, you're right. Yes, that's going to be a useful one. I'm sorry, the new number 3 that's specific to a rhombus.
Diagonals bisect opposite angles.
The diagonals bisect opposite angles, and the opposite angles themselves are congruent as well. Both very useful facts, because if this angle down here is being bisected and this half is 38, what's the other half?
38.
Also 38. So angle 3 is 38 degrees. But then if I jump over to the opposite side where 4 and 5 are sitting,
They're all 38.
they're also 38. So 4 and 5 are also 38 degrees. Now, what that doesn't help me with is my angles 1, 2, 6, and 7, because they are attached to this opposite diagonal here. So I have to get a little bit clever. I have to then think about it in terms of a rhombus. I need to kind of temporarily ignore the diagonals. So what that basically means then, let's say I jump down here to this one where the 38 degrees is. If both of them are 38 degrees, what is this entire angle? The
76.
76. So if this entire angle here in this bottom left corner is 76, and a rhombus is just a unique type of parallelogram, wouldn't this angle here and this big angle up here, again, ignore the diagonal inside, but this whole angle up here, wouldn't they be supplementary since they're consecutive?
Yes.
Sure. So this big angle up here, we would get by taking 180 minus 76, which gives me, I think, 104.
Yeah, 104.
So this entire corner, upper left corner, is 104 degrees. Now I can say, okay, well, let's bring those diagonals back in. And as we mentioned earlier, diagonals in a rhombus bisect opposite angles. So 1 and 2 are just equal halves of the whole 104.
52.
They should each be 52. And using the neat little trick we used earlier for our 38ths, angle 6 and
52.
right, because that whole opposite angle should be a total of 104. Also being bisected, they should both be 52s as well. So it is tricky. And I wish there was like a trick that I knew, like a shortcut to figure out which angles to find first. I don't. I struggle through these two from time to time, depending on what information I start off with. As you notice there, I didn't even find the angles in, in numerical order. I bounced around. So usually it helps to find the ones that you know for sure, and then hope that those help you find the ones that you're not quite certain of. Excuse me. All right, last one here on the rhombus, or last rhombus, I should say. We're given another diagram here, some information above it. Looks like ZY is 34. WY, which is the entire diagonal, is 38, but using Logan's trick from earlier, knowing those diagonals are being bisected, half of 38 is 19, I think. So WV is 19, VY is 19, makes up that whole 38. And then the measure of angle ZXY, it's up here, part of this little corner, is 34 degrees. We're going to use that diagram then to help us work through and find a mixture of sides, or segments, I should say, and angles. So I'm going to start with the sides first. WZ,
34.
34. Why is that?
Is there room around it?
All sides in a rhombus are congruent. One side's 34, they're all 34s. Next up,
19.
19, because we already kind of broke that diagonal in half already, split that 38 into 2 equal parts. Then we get into ZV. Now that's where we have to be creative and say, all right, well, there's a triangle in here, because I don't know anything about the second diagonal yet. So I go in here and I realize that, well, because these are diagonals in a rhombus, they intersect at exactly 90 degrees. And from there, ZV is one of the legs in that right triangle, of which I know the other two sides, the second leg and the hypotenuse. So similar to what we did up above, we can use the Pythagorean theorem to help us find that measurement. So it's a leg, so I'm going to use x to represent it again. X squared plus the second leg, which is 19 squared, equals the hypotenuse squared, so that's 34 squared. And I'm going to solve. This is beyond my capabilities on perfect squares. What's 19 squared?
361,
361.
1156.
And 1156 for 34 squared. Subtract 361 from both sides. Get x squared equals
795.
795. Take the square root of both sides. I get x. Oops, wrong color.
28.2.
28.2. Don't forget though, x was representing our ZV. ZV then is 28.2. ZX then, if you look at the diagram, is just the entire diagonal.
56.4.
Good, so we double the half that we have, we get 56.4 for the whole thing. So that takes care of the missing segments. Now we need to go in and look at our angles. Zoom out here a little bit. So first one we have is angle WXZ. So WXZ is right here adjacent to the 34-degree angle that we have. I happen to recall that diagonals in a rhombus bisect the opposite angles, which means diagonal ZX is bisecting angle WXY. I know 34 degrees of it. That is half. What's the other half? $34. 34 degrees as well. Then looking at my diagram again, I'm looking for angle, the measure of angle WVZ. So WVZ, which is right there inside where the diagonals intersect. Be 90 degrees because the diagonals in a rhombus are perpendicular. And I keep up the good work here. I'm looking for angle ZYW. ZYW. Now, we have a couple different ways we can find it. I'm going to do something maybe a little unorthodox, but what I'm going to recognize is, since I know this 34 degrees up here in this section, which meant that this one here that we answered was also 34 degrees. And since this big angle up here is opposite this big angle down here, they're congruent, which means these two angles are also 34 degrees. Now, that doesn't help me with the angle ZYW that I'm looking for, which is right here, but conveniently inside the triangle we highlighted earlier, I now know two of the three angles. I have 90 degrees, I have 34 degrees. What should the total end up being? It should be 180, so subtract 90, that gets us down to 90. Subtract another 34, be 56. So angle ZYW is 56 degrees. And then the last one it's asking for is angle XYW. XYW. Well, similar to what we did with the 34s, those diagonals are bisecting the opposite angles. That must mean the other one is 56 as well. So I would suspect that if anything's going to trip us up, it's probably going to be the angles again, just because there's so many. But at least this time, a lot of them appear to be the same. Since there's a bisection going on in each corner, you know that they're both the same on either side of that diagonal. And opposite angles are congruent, so technically you know 4 right off the bat, if you know 1. Also, all the angles inside are always going to be in the middle, 90 degrees. So hopefully the angles today will be a little bit easier than yesterday's, hopefully. If not, that's why we'll do some extra practice. Any questions on rhombi? So quick summary before we jump to the back side here. A little bit of kind of logic statements here. Parallelograms. Technically, everything we've done so far has been considered a parallelogram. A rectangle is a special type of parallelogram. A rhombus is a special type of parallelogram. A rhombus is not a rectangle. A rectangle is not a rhombus, but they share that connection with both being parallelograms. So we want to make sure we don't accidentally overlap some of the rules. I say that, however, before we move on to squares, which you'll notice is a special form of all three. It shares all the properties of parallelograms, rectangles, and rhombus, because by definition, a square is a parallelogram, it is a rectangle, and it is a rhombus. It's just a very, very special hybrid version of all three. So what you'll notice here, nothing extra to write because it's just recycling all three that we've had before. So it's a parallelogram, it's a rectangle. Actually, watch me get fancy here. So it's a parallelogram, which are these standards right here. It's a rectangle, which encompasses these two right here. And it's a rhombus, which includes these three down here. So again, you don't have to get that fancy. Sometimes I just like to show off. But what's nice is there's nothing new to have to learn for squares because it's just everything else. So we get to dive right into working through some of these squares here, or at least a couple of them, because they don't get very interesting. Because since they are so unique, a lot of the things are already kind of predetermined. And I'll show you what I mean here. So on our first one here, we are told that if ABCD is a square and AD, which appears to be this left-hand side, oops, wrong tool, is 11, find each missing value. We have some sides, we have some angles. So I'm going to suggest we start with the sides first. What's side BC? 11. Because similar to a rhombus, all sides are congruent. Okay. What about AC? Careful, AC is a diagonal. So then I have to say, well, shoot, I need to think about this in terms of a triangle. And then if I apply a little bit more of what I know, since it is a square, DC is also 11. And because a square is technically a form of a rectangle, that means every corner is exactly 90 degrees. So I have a right triangle of which I know both legs. I'm looking for AC, which is the hypotenuse. I'm going to use the Pythagorean theorem. I have 11 squared plus 11 squared is going to equal x squared. Eleven squared is 121 plus 121 equals x squared. 121 plus itself, 242. Take the square root of both sides. believe we get 24.
15.6.
Oh, no, I'm wrong. I'm looking at the next one.
15.6.
15.6. Spoiler alert, I ruined the next problem. 15.6 equals x. Of course, x was representing AC. So AC is 15.6. What about BD?
Would you work it the same way you just worked AC?
I'm glad you said that, but if we worked it the same way we did AC, I'm still going to have two legs that are 11s
Mhm.
since it's a square. So shouldn't I come out with the same answer?
Yes.
And hopefully that doesn't shock us, because isn't a square a special type of rectangle?
Mhm.
If you look up above, for the rectangles, diagonals are congruent, which means AC and BD, both being diagonals, are going to be the exact same length.
Mhm.
But yeah, you would technically do the same thing, but because it's literally the exact same steps, it's going to give you the exact same outcome, which is 15.6. The last one there then, EC. EC is only part of diagonal AC, but
15.
yep, absolutely, half of 15.6, because being a parallelogram, diagonals bisect each other.
7.8.
So we'll get 7.8. Good. Next up, we have our angles. Angle DAB. I'm mildly disappointed that nobody actually dabbed there, but whatever. 90 degrees, because a square is a special type of rectangle, and rectangles, all four angles are 90 degrees. What about AEB? Also 90 degrees, but for a different reason. A square is also a special type of rhombus, and the diagonals in a rhombus are perpendicular. What about CBD? Be 45. And we can come to that conclusion very quickly, because if all four corners of a square are 90 degrees, and the fact that it is also a rhombus, meaning that the diagonals are bisecting the opposite angles, half of 90 is 45 degrees. What about BAC? Also 45. In fact, you'll notice for any square, literally any square, all four corners are going to always be 90 degrees. And when they're bisected by the diagonals, those bisected portions will all be 45 degrees. Which is why there's only two specific examples for a square on this one. You run out of variety. Second square here, it's telling us the PQRS is a square, and TR, which is inside here, is 17. Find each missing value. Well, let's see. PR, which is the entire diagonal.
24.
Not, how'd you get 24?
Double 17.
Oh, careful, it'd be 34. But yes, you would double 17. Since we know half of that diagonal, doubling it should give us 34 for PR. What about QS? Also 34, because the diagonals are congruent, because a square is just a fancy rectangle. QT would be 17, because the diagonals are still being bisected. And PQ, we'll have to do some work on this one, because PQ is up here at the top.
Okay.
We don't actually know any of the outer sides of this rectangle. We did a lot of the diagonals inside, but we've got a little bit of work to do. And so I'm going to highlight this little triangle sitting at the top of this square. And luckily, since this is a rhombus, the diagonals are perpendicular.
180 minus 90.
Careful, I'm not looking for an angle yet.
Mhm.
So angles would be the 180s and the 90s.
Mhm.
I'm still looking for a side, which is PQ. If I think about it though, all the diagonals in here were equal to each other and bisected, which means all these segments in here, I guess I could have done this, are all 17s. And I'm looking for the hypotenuse in this little triangle that I highlighted here. So I can use the Pythagorean theorem to say 17 squared plus 17 squared, which are the two legs, equals the hypotenuse squared, which is, I'm going to use x. What's 17 squared?
289.
289. So I have 289 plus 289. What do you get when you add those together?
578.
578. And then square root both of them. We get x equals
24.
24. Perfectly, right?
20. Yeah. Exactly.
Don't forget though, the x was representing PQ. The side of the square is 24, which, if you think about it, is all four sides of that square. When I expand out here to take a look at the angles, kind of already spoiled part of the surprise because I said the angles in a square are rather boring. A lot of 90s and 45s. Angle PRS,
90.
careful, PRS
Oh, 45.
is 45 because it's part of where the diagonal is bisecting that corner. What about STR?
90.
Be 90, but not because it's in a corner, it's because the diagonals are perpendicular. What about PSR? Be 90 because it's a corner of the square. And QPR will be 45. So again, not a whole bunch of examples for squares because like I said, the angles in a square are only going to be one of two things, 45 degrees or 90 degrees, depending on which angles you're looking at. All right, last four here, forcing us to set up some equations, make sure we know what it is we're looking for. Odds are it may not just be the variable that's in there. It is going to have us determine the relationship based off of what type of shape it is. So taking a look at number 8, I'm being told that it is a rhombus, and I need to find MP. Well, odds are probably want to find X first. It might help us. So what do you know? Look at where the two expressions are. They're opposite sides. Well, they are congruent. In fact, it wouldn't even have mattered if they were opposite because all the sides in a rhombus are congruent. So we can very safely say that these two sides must equal each other. So 9x minus 77 must equal 3x plus 7. Going into solving mode here, I would subtract the 3x from both sides. Gives me 6x minus 77 equals 7. Add 77 to both sides. Get 6x equals 84. It says with only a little bit of confidence. And then last but not least, divide both sides by 6. You get x equals 14. But be careful. It's not asking for x. So important, but not what I need. What is it asking us for?
Angle MP,
Oh, careful, not angle,
side.
side MP. Well, if you notice, MP doesn't even have an expression attached to it. Should that matter?
No,
Why not?
because they're all the same, each side.
Every side is congruent, so it doesn't matter whether it has an expression on it or not. All 4 sides of that rhombus are the same. So we can pick either one of those 2 expressions we do have to drop our x in, because once we find that value, we find our value. So I'm going to say PO equals 3x plus 7. I drop in my 14, so 3 times 14 plus 7. I believe we get PO equals 49, which means that's the same as MP, meaning MP is also 49. Number 9, another rhombus, this time working with angles. We're looking for the measure of angle FED. Probably gonna have a little bit of work to get there because it's all the way over here in this corner and I have no information for it yet. But if I can work out what X is, I'll be able to work out something about this other corner in the rhombus. So that's gonna be my main goal, find X. What can I do with these 2 expressions? Why can I set them equal? They are being bisected. The diagonals in a rhombus bisect the opposite angles. Well, bisect means cut in half means 2 equal parts. So these 2 expressions should be equal to each other. So 8x minus 20 must equal 5x plus 1. I'm going to subtract 5x from both sides. I get 3x minus 20 equals 1. Add 20 to both sides. I get 3x equals 21. Divide by 3. I get x equals 7. I'll write it off to the side here. Now, we need to find angle FED, which is not attached to either of these expressions. So I've got a little bit of work to do here because only way I can figure out this angle over here that I'm looking for, I really need to know angle CFE because those 2 angles then would be consecutive, making them supplementary. So I need to work out what this big angle is here. And to do that, if I know half of it, I'll know all of it. So going to be a bit of a roundabout process here. I'm going to use angle CFG, which equals 5x plus 1. I'm going to pull out the x and put in the 7. And that tells me that angle CFG 5 times 7 is 35, plus 1 is 36. That's half of that corner. If I double it, I believe I get 72. So angle CFE would equal 72 degrees. And then I tell myself, well, angle FED and angle CFE are consecutive, therefore supplementary. So if I take 72 from 180, I get that angle FED equals 108 degrees. That one really made us work for it, because I had to find half of an angle I wasn't even interested in, so I could then double it. And then once I knew that angle, knowing that it was consecutive to the angle that I wanted, I had to take that sum, subtract it from 180, and what was left was the angle that I was looking for. What a very roundabout way to get to our conclusion. Numbers 10 and 11 should go a hair faster. Number 10 tells me that STUV is a square with SW being 2x plus 3, excuse me, plus 13, and WU being 8x minus 41. Find VT. Well, what can I do with those two expressions? I can set them equal because the diagonals in a parallelogram bisect each other, which means these are just two equal halves. So 8x minus 41 equals 2x plus 13. Subtract 2x from both sides. I get 6x minus 41 equals 13. Add 41 to both sides. I get 6x equals 54. Divide by 6, I get, hopefully, x equals 9. Almost said 7. That was my bad. But x isn't what I was looking for. I'm looking for VT. Well, VT is the opposite diagonal. Should that matter though? Which diagonal I end up finding? No, because the diagonals are congruent, because squares are just rectangles too. So if I can figure out half of the length here, I can figure out the whole length, which then leads me to my conclusion. So I'm going to use SW. Plugging in my x, so I have 2 times 9 plus 13. Oops. So SW, 18 plus 13, I believe is 31. Well, SW is just half of SU, but SU is the same as VT, so really, all I need to do to find VT is just double that 31. So I believe I get 62. And last but not least, number 11. All we need to do here is solve for x, which is nice, but all it did was give me one expression. So we can't just say set them equal because there's only one of them. But I am told that this shape is in fact a square. What could I do here? Multiply it by 2 to set it equal to 90. That would work. You're actually doing one more step than you even have to. So your head's in the right place, but let me ask you this. You know that corner is 90, right? What's that diagonal doing to it?
Bisecting.
It's bisecting it. So if I wanted to, could I throw out doubling it and just say, well, if half of 90 is 45, could I just set it equal to 45? You would have gotten the same answer either way. So I don't want to say you're wrong. It's just, you do an extra step, which is fine too. It's not a competition. But me, I like to try to find the fewest steps possible. And since I know that that corner is 90 degrees and it's being bisected by the diagonal, that must mean that that half is set equal to 45. Then it's just a matter of solving a two-step equation. Subtract 3 from both sides. Leaves me with 7x equals 42. Divide both sides by 7. I get x equals 6. And that's all I needed for this one. So squares, I would argue, may be the easiest only because you can assume so many things to be true automatically. Rhombus, a little sneaky because if you try to accidentally apply one of the unique rectangle properties to a rhombus, it doesn't necessarily translate. Now, they all share the same rules of a parallelogram. So those 5 that we started with yesterday are fair game for any shape in these quadrilaterals we've covered thus far. But be careful, don't mix the rectangles, 2 special ones, and the rhombis, 3 special ones are not intermingled. They're separate. So tomorrow, we're going to do a completely whole different quadrilateral, which is a trapezoid, which says parallelograms. What are those? We don't follow those rules. We do our own things. But for today, those rules continue to apply, which will help you through the assignment.